while we get started, I'd like to encourage everybody, stand up, move around a little bit. I don't know, shift in your seats, do something, anything, and I have a handout, so you know it's going to be fun. You're not allowed to look yet, all right? Pass one, take one, pass it down, up the aisle we go. Do not look, do not peek. It won't be any fun that way, all right? So, now, get up, get stretched, and get your heads in, because I've already justified what we're going to do, so we're just going to get straight into it. We're going to have some fun. And prepare your evaluators. Everybody has their REPL session in? We're good? Yeah? First execution? Set it? Remember it? We're good? Okay, so trees. Everybody knows trees. Does anybody not know trees here? All right, good. So most people, when we're working with trees, including APLers, we have to work in some way with this. And of course, you're welcome to stay standing during this entire thing, or you can sit down. It's up to you. Most people think of trees like this. So we've got a top root node, and then we have some siblings going, or some children going down from there. And then from there, those children can have children and so on, and we have a bunch of descendants. And we have some siblings. So at the root node, there's one, the Adam node, if you will. And then there are some children there, Seth, Ham, or something like that. And so you can have the siblings next to each other, and then they go down. And most people also know about the depth of a tree, right? So a tree can have its depth. And here we're going to be index origin 0, so we're going to start at depth 0, and then we go down from there, all right? Now, unfortunately, this is where most people sort of stop thinking about trees, or they start using what they've learned in their university. And if we want, we can basically say this talk can be rewritten as saying everything you knew about trees in university, forget it, you're wrong. Or, we're doing this the APL way. And so what I'm presenting here is a way in which we can approach these trees, keep our asymptotic benefits, but think about this stuff in the way that we've been told we need to think about problems. So Martin said vectors, arrays, everything like that. We need to make sure that we're doing our reads correctly. And in addition to that, I think I heard some people mentioning that I don't really put very much information on my slides. So, and I use a lot of them, right? Just go bang, bang through them. And I couldn't help myself. I'm sorry. I apologize. But you asked for it. So here goes the slide. So that's the same tree that we had before. But now we've reorganized it a little bit. So at this point, what we really need to do is we need to think about how are we going to rethink about what a tree is when we approach it, right? So it's going to require a little visualization and a little work from there. So here's our tree, same tree that we had before, but we've reoriented it. And this reorientation is critical because one of the most common traversals that we see in a tree is called a depth-first pre-order traversal. And what is that? Well, APLers might begin to figure this out, so begin thinking a little bit about what this might be. But here we can give each of these nodes an identity, an ID, based on the depth-first pre-order traversal. And it just so happens that this depth-first pre-order traversal, this DFPT, corresponds to visiting those nodes in this order that we visualize them here. So you touch each node and then go down the leftmost child, and then you touch that one, and you go down from there, and then you pop back up, and then continue down along that path, right? And what we can do is we can look at this, and we can reorganize this the way we would normally think about a tree. I call this the ADT way, or the recursive data type way, or whatever you want to call it. And this is, in fact, an APL expression. It's just been thrown out in a little longer form, right? So our root ID is 0, and we go down from there, right? Now, at this point, if anybody begins to get confused, lost, or the like, raise your hand and I'll slow down a little bit, okay? So, because we don't have to get through everything, all we need to do is make sure you begin to get the intuitions for how to work with these trees, because then you can figure everything out from there. And so if we take this, we can also think about what is the depth of this tree. And so here is the depth of each of the nodes in this tree going along. And you'll notice that this sort of corresponds to the indentation level in the tree like this, right? So if we begin to represent trees in the traditional way in which we can think about them, and we're going to begin looking at this from the quad XML JSON point of view, we've got the way we might write it with nested vectors. But as we've learned, nested vectors is a bit of a problem, right? We have too many pointers, header overhead, and we begin to run into memory fragmentation. We can't control the locality of our data. It's all a mess, right? So it does have this benefit that the IDs are just the end list of the ADT. I like that. That's kind of a neat little solution. But if you're familiar with the quad XML format and the quad JSON format, there is another option, right? Does anybody know what this option is? The structure? The way we might encode a tree in the quad XML format? Yeah, and what's the first column of that matrix? I'm sorry? Level. Yeah, right, exactly. Just this depth vector, right? And that depth vector is sufficient to encode all of the necessary structural information that you might ever need about the tree. And it has another advantage. What are the size of the integers likely to be in this tree? Right. Because the size you need is essentially logarithmic to the tree, or based on the depth of the tree, not based on the number of elements in that. So this is a very compact, efficient way to represent your trees, but it has a problem. And what is that problem? I'm sorry? Well, the data is going to be missing in all this because we're just talking about the structure, right? So yes, we're missing the data. That's a good point. We are assuming that you'll have other variables which correspond to these structures that have the data in it. So we're just focusing on how we work with the structure of the tree here. The problem here is that we have a linear dependency. How do we find our child? So if we go down to node 14, how do we find out that that node 14 belongs to node 17? We have to walk somehow up this tree. And how many nodes might be between node 14 and 7 if we don't know, how they're arranged? Any number, right? So actually it's linear to find your parent here in the worst case, because we might have to potentially walk the entire tree in order to find our parent. So that's not so great. Now we can restructure this a little bit. If we take our nodes and we sort of reorient them again in this structure, we can create what's called a path matrix. And this is an optimized path matrix, and you can read one of my Array 2016 extended versions of that paper to see how we can construct these. But the idea is if we represent our tree like this, we can just sort of push over the parents across this matrix that we're building, right? So every one of these is a parent, or has 0 as a parent, and then we can propagate that again through the next section. And so if we go down the line and do this, what do we end up with? Can somebody see the pattern? So if we go up these columns, what do we find? Right, we find the parent. So not only that, but the parent is a constant time reference, right? And given any two arbitrary nodes, these prefix strings represent a way for us to identify the location of every node relative to any other node in the n-dimensional space of the tree, if you will, right? And so it's very, very easy to independently compute the things. And so now basically what we've done is we've separated out the issue, and we've removed that dependency on the ordering of the nodes in some sense. But there's a problem with this one, and we should immediately be thinking, what's the problem with this representation, and what is that? You guys should all be thinking 2 words. Whizful, right. Because the size of this path matrix is n times the depth of the tree, which is quite a bit larger than just n. So how can we optimize this? We can compress this representation, right? And this is a common representation that scientific computing and HPC people have been doing for a long time, is you can represent your nodes based on a parent vector. So for each element, what do we have? We just have the parent and the sibling, and these are pointer vectors. So what they are is each element corresponds to one specific node in the tree, and its value, the value of that element, is a pointer pointing to the index of another element in that vector, which is its parent or its left sibling. So we have the P and L vectors here. So let's go through this. What's the parent of 0? So everybody goes to neg1. The HPC community goes to neg1. The scientific community goes to neg1. They all use a null element, and that's a legitimate way we could do that. There's one problem with that. Yes, exactly, the indexing. So neg1 is not a valid index in APL, which means that now you have a potential index error if you try to use these, because these are pointers. So neg1 is not in the index domain of the vector. So instead, because we're working with trees, I prefer self loop. So just refer to yourself. And you'll see why I prefer this in a future slide. So now, node 1, let's go through this. What is this? 0 and 1. Right. Next one? 1, 2, yep. Yep. And number 4? Nope. 3, 4, because it's the most leftmost. So it points to itself there, right? And we go through this. Are we getting that? If we have to spend the rest of the talk just on this, we'll do this, because this is the most important, critical part of this thing to understand. Right? That's the left sibling. So we have the parent vector and the left sibling. Right, so if you are all the way to the left, it's the same as being all the way to the top of the tree, and so you make yourself your own left sibling, or your own parent. And there's another interesting thing about this. The depth vector had a dependency on the order, right? The parent-sibling relationship fully encodes the structure and order of the tree, but there's no ordering dependency on the elements. So as long as we recompute the pointers correctly, we can reorder these elements in any order that we want, right? We don't have to have 0 as the first one, right? We could put 0 somewhere else, and we just update all of our references to 0 to point to index 15 or something like that. So this is an important property of this representation, that we can reorder arbitrarily all the elements in this thing, and we don't lose the structural information of the tree. This is critical, actually. And additionally, sometimes you have a problem where you don't care about the ordering of your siblings, right? You're more egalitarian, maybe a Western-style sibling-family relationship than an Eastern-style. So you don't need the left vector if you don't want to. And there might be good reasons, and I'll talk about these, why you don't want the left vector. So if you turn over your sheets, you'll find your nice little cheat sheet for this slide. This is going to be necessary for you to help remember what kind of structures we're working with for the rest of this talk. So, this is the first idiom, adding a node. And now we can begin to see why this is so much fun in APL. Because what we're looking for, and what we find, is that all of these standard ways that we might want to manipulate our trees correspond more or less directly to APL primitives. So this is the easy one. Catnate gets, it's an idiomatic expression in Dyalog APL. It has good asymptotic behavior, and we can just, if you want to add a new node into the tree, tack it onto the end. Done. Right? So this is the simplest one. This is the one I give you for free. Any questions about this one? Does this make sense? Are you beginning to see this? Sorry? Yeah. You could just shout out. Yeah. So in this, what we would put as the left argument would be like P or L. And then we would give, so if we wanted to add a new child to the root node, we would say P catnate gets 0. So we've added a new element whose parent is the root node. Right? It would be added on the end of the parent vector. Yes. And that's actually important, because since our parent vector does not have to be ordered, we can actually put it anywhere. So for instance, if we wanted to put that node in the root, what we pick for the L value, when we concatenate the L value, is where it decides where horizontally it appears in the tree. Right, exactly. So if we wanted to insert this into the middle somewhere, we have a left linkage that we have to link up. So we have to do 2 updates to insert it into the middle. Inserting it on the tail end is 1 update. If we want to put it at the head, it's 2 updates, or anywhere in the middle, it's going to be 2 updates. You have to insert it like a linked list. So any of you who are familiar with linked lists insertion in the middle, you have to do something like that. Fortunately, it's not as bad because in most linked list insertion algorithms, you have to scan to find your insertion point. Here, finding that insertion point just happens naturally. So now what about deleting nodes? Anybody who is at the Iverson College should be able to know this one. So this one, I'm sort of playing a trick on you. This is the hardest one. Any node, any arbitrary nodes that you're deleting, there's this idiom for doing this. I call this the garbage collection idiom. So on the left and the right of that train there, you've got the obvious stuff, right? So you've got, on the left, the set of nodes you're going to delete, selected by a Boolean mask, and then on the right, you're going to select the ones you want to keep and filter out P, right? So that's easy. But the problem with that is that now that we've deleted some nodes there, our pointers are all irrelevant now. They might be messed up. We can't guarantee that they're pointing to the right things anymore. So what do? Well, interval index comes to the rescue, and we can easily recompute this. And I don't think we have time right now to explain this, but I would be more than happy to go into excruciating detail on this one on a napkin at lunch for anybody who would like to learn more about that. And updating is trivial. It's just assignment or at. It's, you know, if you need to update the linkages, move an edge around in the tree, you just use add or bracket indexing. Traversing, this is an interesting idiom. So if we want to traverse the tree, this is the idiom that we use. So we run an index replacement along a pointer vector, and I is like a squad that indexes over the major cells, if you will, and is commuted. So you can say something like x, I, n, and that'll be x indexed by n. And so we can use the at with the fixed point operator and allow us to walk up these pointer vectors, which we'll see in an example. And then selection. So one of the things we need to be able to do is query our trees and find things. Unfortunately, the Dyalog team has done a number of things to make these primitives very, very, very fast. So you can then use a Boolean set of operations to collect up, mask over, and select your elements, and then use something like where to identify the specific ones. And those have very, very, very good performance. So here's a basic example, right? And this is starting with a p vector, we can then recover our depth vector d that you have on that paper. And so we start by sort of seeding our d with an initial value, and this is to deal with our edge conditions when we hit the root. And then we run this little function to a fixed point. And so we start with the parent vector, and we look up our parent's parent, and we see whether that's changed. And if it's changed, it means we haven't reached the root of the tree yet. So we add 1 to our depth. And then we repeat with the newly extracted parent vector. And we continue iterating on that until our parent vector doesn't change. So what happens is if you look at your sheets, you'll see that path matrix. Every one of these little elements is going to be traveling up a virtual path matrix. Right? It's like walking up your column in that path matrix, going from parent to parent to parent. And we're just counting how long our column is, if you will. And that gives us our depth. And you'll notice this is intentionally different than your standard tree traversals, because the standard tree traversals start at the top and you recur down the tree. We start at the bottom and go up. And the reason is for vectorization. Because if we start at the bottom, we know exactly how large our initial set is going to be because we start at the leaf nodes. So we walk up from there. And that allows us to fix our parallelism at some level. And this makes it much easier to execute this and schedule it on a GPU. And it allows us to use lightweight SIMD parallelism instead of relying on a heavyweight SMP fork join, type mechanism like isolates. Any questions about the depth here? Could anybody write this again if I took this off the screen? But the idea here, the idea to remember is this is the sort of canonical way in which we do this traversal, right? So we basically start at the leaf nodes, or every element in P, and we just start walking up from there, right? So we start at P, and every P is going to be somewhere, and from somewhere you can get to your parent. And then you just continue to walk up from there and visit all the rest of your ancestors until you reach the root node. And because we've put that self loop on the root node, we're going to just reach a fixed point eventually at our traversal. And I've been asked at times, well, how do we go down the tree? And the answer is don't do that. But occasionally you do need to do that. So for instance, here's one of the compiler passes. Is I need to figure out if you say x gets 5, I need to know that x is associated with 5 as a name. So this builds up a binding table that says for every given node, what value is the binding pointing to, right? And in this case, what I do, the way you can read this is if you ignore the first fixed point limit, inside that index, right, we're starting with every element, iota tally p, that's all the elements, and then I say, all right, let's get I, and I is going to be all the nodes, and see that where, instead of saying interval index of, in this domain, that iota underbar now becomes the nodes, or the IDs of the nodes, and so you just read it like that. So you say the nodes where the type of its parent is 1. Right, and actually, I should have swapped the t sub p and equals 1. I should have commuted those. But that's the way. So we have a type vector, t, which is the same length as p, but contains a numeric ID indicating what's the type of that node. So the type of binding nodes in my compiler is 1. So I say, look for all the nodes whose parent is a binding node. That's t sub p equals 1. And I happen to know that in my AST, the binding nodes each have exactly one child, which is the value which it's binding. And so what I then do is I say, well, let's just change the parent to point to its child. Right? So I say, look up all the children, grab their parents, and at their parents' location, replace that with me, or the child. So now I've essentially walked down the tree by going up the tree, if you will. And this allows me to build up the binding table. And then everything after that fixed point is running to eliminate nested chains of bindings. So a binding, you could have x gets y, gets z, gets 5. So then if I do this, x is going to be bound to the node that has y as the binding, and y is going to be pointing to z, and z is going to be pointing to 5. And actually in my binding table, I want x, y, and z all to point to 5. So that fixed point there, it uses that traversal pattern. So you remember the traversal pattern that we covered, right? That traversal pattern of index at some condition to a fixed point. And so we have an index at type equals t of sub omega. So what we have is the binding table, which is another sort of pointer vector. And we just look and say, well, are you pointing at a binding node? If you are, instead point to whatever that binding node is pointing to. And we just recursively do that. Well, we don't really recursively do it. We just iterate over that using the fixed point. But we repeat. So here's the operation to lift functions. And you don't have to necessarily understand everything going on in here, but this gives you a flavor of what you might do. So my I is where I figure out what nodes I'm going to work on. So in this way, it's the nodes whose type are 3 and that are root nodes, or that are not root nodes. That's the way to read that. So in this case, I'm finding all the functions which are of type 3, that's the function type, and I look for all the ones that aren't at the top level, because those are the ones I need to lift. And so p not equal iota of tally of p is the idiom for saying you're not a root node. And this idiom here is actually really, really important. The L gets this s plus iota at. One of the hardest parts of working with these trees is the L vector. I consider the L vector, I would like to find a better way to do it. I'm listening to anybody who would like to change it, because the L vector is where most of your bugs are going to show up. And so it's important to be idiomatically correct about the way you write your L vectors, or just get rid of them if you don't need them. And what this does is, what I do is when I lift the functions, I'm going to have to replace where they were with a variable reference. So I have to generate and create a new set of variables. And you can see down here, all the rest of it is just catenating and indexing to make everything point out right. So I'm going to create the new variables, and when I add them, that's the PL gets operation. So I'm just going to add a whole bunch of new variables, and they're just going to point the right way. Their type is 10, their subkind is 1. That's not bad. The n is the reference, so it's going to point back to the lifted function. So it's a variable that refers to the function that I'm lifting up. And the rest of this is all making sure that the L vector is in the right place. And I don't have time to explain it, but I would very much like to explain what that L thing is doing, because what it essentially is doing is or how it's doing it. But what it's doing is it's taking all of the left pointers of the original lifting functions and pointing them at the new variables first, before we lift them up, and so that we can do some computations with that. And that's a technique that I've developed which helps to make sure things all go in the right order. And we can do this by pushing down as well. So we can lift up, but we can also push down. So here we've wrapped returns. So we say all of the nodes of type 0 and 2, or that are type 1 and of subkind 0, and they also have to have a parent whose type is 3 and 4, and they have to be the last, or the rightmost sibling, the one that's all the way to the right instead of all the way to the left. And there's a little idiomatic expression for computing the rightmost element instead of the leftmost element. And then we say, okay, and then we want to take each of those nodes, wrap them with another node, and then insert that node in the middle of the tree. But we've heard a talk from John Scholes on how defunds work. So you guys immediately identified the bug in this program, right? Because there is a bug in this program, and it's here. Yes, obvious. I'll give you a hint. John Scholes lamented about this problem. Oh, no. The code is syntactically and mechanically correct. It's just semantically doing the wrong thing. Oh, yeah, but the global assignments are okay in this case. However, you're getting close. What was one of the other things he complained about? Do we return X or Y here? Yeah, and what does our return expression selector do? It only grabs the rightmost element. So it would wrap Y in a return value, but it would leave X alone. And so this function, if we compiled it with this wrap returns, is going to return Y instead of returning X. That's not going to work. So we have to make sure that we also wrap things that appear at the top level of our functions that are of the right type, and wrap those as well so they return before we ever hit a Y or something like that. And so this is the kind of bugs you can also get. And you have to learn how to think about the bugs as well as how to think about the code, because the bugs are going to be different when you misunderstand something, because you're approaching solving your trees in a different way. And I know this was all very, very quick and so forth. So, you know, I'm going to talk as much as I can with you. If afterwards, I'm happy to talk with you. Just, you know, catch me, and we'll spend as long as it takes to make sure that you guys can do this on your own, even by Skype, whenever, you know, preferably when I'm not sleeping, but, you know, that's not too bad. So the takeaway that I always tell the computer science community when I talk to them about this is more or less this, right? So that's what the CS community gets when I talk about trees. So what does the APL community get? So don't be afraid of trees, but don't try to do trees the way everybody else does, because that's boring. Instead, there's actually really, really nice ways to manipulate your trees in APL. And when it clicks for you as well, and you begin to be really, really happy about this, don't gloat too much, because it'll be tempting. So, thank you.